Okay, so we have a way to test for independence here. A and B are independent if and only if the probability of A given B is the probability of A. Now, it turns out that we have some other ways to test for independence. Turns out A and B are independent if and only if the probability of A and B is the probability of A times B. I'm sorry, the probability of A times the probability of B. Okay. Now, don't screw this up. A lot of people will just tell you that the chance of both A and B occurring is the product of the two chances. That's not true in general. This is only true if A and B are independent. Okay. It's only true if A and B are independent. Okay, but let's prove this. So here is proof. So the probability of A I can write as the probability of A given B. This is if and only if A and B are independent, right? We're assuming that A and B are independent. We're trying to prove then that this is true. Okay. So if A and B are independent, we know that this is true. And then now, by the definition of conditional probability, we can write this as the probability of A and B divided by the probability of B. This is by the definition of conditional probability. And so all this means that probability of A and B must be the probability of A times the probability of B, right? Because I've got this is this. And then so if I multiply through both sides by the probability of B, it comes up here, and then you got the chance of A times the chance of B. Okay, so that's got to be true. That's really good. That's a useful way to then get the chance of these two events. If you have independent events, then the chance that both occur can be computed simply as the product of the chances of the individual events. It's really useful. We have another way to test for independence. If A and B are independent, or A and B are independent if and only if the chance of B given A is the chance of B. And that seems to sort of seems to make some kind of intuitive sense, I think. Certainly if A is independent of B, then B should be independent of A, I guess. So we can prove this real quick. Here's the proof of that. Start with the left-hand side there. Probability of B given A. This is the probability of B and A over the probability of A. This is by the definition of conditional probability. Conditional probability definition. Okay, but now, since if we assume independence, okay, or if and only if A and B are independent, then this is, I can write this top here as the chance of B times the chance of A. Divide that by the chance of A and get canceling, and there we have it, folks. Probability of B is the same as the chance of B given A if they're independent. So we have three equivalent ways to test for independence. Okay, they're also useful not just for testing for independence, but they're also useful for if you're given that some events are independent, then they're useful for computing probabilities. So the chance of A given B is the chance of A. The chance of B given A is the chance of B, and the chance of A and B, which is, we'll typically write this now with commas. This is the chance of A times the chance of B. Okay. So here's something that's sort of interesting that may or may not help you at all, but that is, I don't even know how to say it, but maybe we'll try it like this. Independence sort of does for intersections what disjointness sort of does for unions. Okay. What I mean by that is that so generally we have the chance of A and B. Generally, what's the chance of A given the chance of A and B? It's the chance of A plus the chance of B minus the chance of their union. And the chance of A union B is the probability of A plus the probability of B minus the probability of the intersection. Okay. But, and that's a big but. But if A and B are disjoint, remember what axiom 3 says. If A and B are disjoint, then the probability of their union is the sum of the individual probabilities. And if A and B are independent, then the probability of A, now I'm going to flip the sign over, okay? See that? Turning it over, the chance of both is now, it's not the sum, but it's the product. Okay? It's the product. Okay? So you can think about it this way. When you add two numbers, and these are numbers, right? The probabilities of events. Probabilities are numbers. When you add two numbers, you're sort of combining them in some way. You're pulling them together. You're making some kind of an amalgamation. You're making something larger than what you had before. Just like when you apply this set algebra operation of union to two sets, right? You're making an amalgamation of the two sets, but you're bringing together everything that's in either one of them, but without counting overlappage twice. Okay. And so sort of saying that the sum of these two measures is the measure of this amalgamation. Here, under independence, if you flip the sign over, you're looking at what they have in common, okay? And it's going to be, this region in here, this event is going to be smaller. And what happens if you take two little numbers between 0 and 1 and multiply them? You get something smaller. So anyway, I think that's sort of beautiful. Maybe you will too.